My name is Friedemann Freund, presenting on behalf of a group of John Scoville, who is working with me here in California, and Pamela Clark and Russell Cox. We are going to talk about some brand new development in understanding the Lunar Regolith, and the question that we want to discuss is whether the moon was ever wet, whether it had amount of water. Now, the basic facts are that since the Apollo time, lunar rocks and lunar regolith are thought to be very dry, bone dry, with often no detectable trace of hydrogen and even no detectable trace of the element hydrogen in these minerals. However, the absence of hydroxyl does not necessarily mean that the rock was dry. And the reason is that when water becomes incorporated into the minerals during crystallization from the magma, it forms hydroxyls, SiOH, and many of these hydroxyls will occur as hydroxyl pairs. During cooling, when the system moves out of thermodynamic equilibrium, there is a very interesting redox conversion taking place in which the oxygen donates an electron to its own proton in the hydroxyl group. And this happens among the hydroxyl pair, forming two hydrogen atoms which combine to form molecular hydrogen. And the oxygen becomes now oxidized to the peroxy state, shown here in blue, which is now a defect in the crystal structure, and the hydrogen molecules are sitting on interstitial sites. Now, molecular hydrogen can diffuse out even of structurally dense minerals like olivine, and then the peroxy are left behind. So I'm proposing that peroxy are the memory, possibly the only memory, of a former water content in a lunar rock. So the hydrogen is moved out here, shown with the arrow, and when the hydrogen is gone, it is only the peroxy that is left. Now, what are the consequences of this particular sequence of solid-state reactions in the lunar rock? So up there in the brackets, you have the past, that traces of water existed in the magma. Traces of water were incorporated in lunar minerals, including those that are nominally anhydrous, like feldspars, pyroxene, olivine, and so on. But then there is this redox conversion during cooling by which hydrogen is formed. Hydrogen, particularly over a very long time of 4 billion years of the moon, much of the hydrogen, if not all of it, can have escaped by diffusion. And then what we have is peroxy as a memory of water is the only memory of the water, and the hydrogen has essentially left. So we would have to, if we want to understand how much water was in lunar rocks during formation, we have to look for peroxy. We don't have to look, and we should not look for hydrogen. And there are several things that come to mind when ultraviolet shines on the lunar rock. The peroxy become oxidized, become activated, and they form all radicals. This creates a surface reactivity. The surface becomes highly oxidizing. That's what the biologists call ROS, reactive oxygen species. This could lead to tissue damage for people that are exposed to lunar dust. But this is a question that is more of medical color. We would like to now look at some physical properties of this UV activation process, and we're focusing on measuring and getting information about the electrical conductivity. So when UV activates the peroxy bond, there is an electron-hole pair mechanism that is being formed. So electron-hole pairs are forming, the electrons become trapped, and the holes, known as positive holes, these are charge pairs that are associated with the oxygen sublattice. And they are highly mobile, and they move at about 100 meters per second. And they have the unusual property that they are able to move out of the illuminated volume, traveling into the unilluminated volume, as I said, at a speed of about 100 meters per second. They flow fast and far. In laboratory experiment, we can show that they move over long distances. In some cases, we have shown that they can move over meters. And the experiment that I will show in a moment, they moved over distances of 20 or 80 centimeters. So we set up, some time ago, just a piece of gabbro, a slice. The dimensions are roughly, let's say, 30 centimeters on the long edge. We shaded it, and we attached two sets of electrodes, one electrode at the edge on the right-hand side, and on the left side, just two electrodes that are exposed to UV light. And we are going to measure a current that is flowing between the illuminated part and the unilluminated part the moment we switch the UV light on. So the UV lamp was allowed to burn in for several minutes or half an hour in order to get up to full equilibrium, and then the window was opened, and as you see in the plot, instantly there is a current flowing from the illuminated part to the unilluminated part, and the current is on the order of something like over 100 picoamps. The moment we close the window, the current goes away. At the end, when it goes away, it slowly takes back towards zero. Now the question is, here we have done an experiment in which we illuminate also the copper, and we might be concerned that the UV light hitting the copper electrodes may have contributed to the current. So we have to answer the question, first of all, can these activated, UV-activated positive hole charges also flow through dust? And can we set up an experiment in which the electrodes that allow for the measurement of copper electrodes are not exposed to the UV light? To do this, we built a large box. Actually, what you see here is a box from U-Haul, and we modified it, and we used a welding arc as a UV source, and we had extra shade, double shade, so that there were absolutely no UV light penetrating into the dark region of this, and there were two copper meshes, about 30 centimeter wide and 15, 20 centimeter long, that were embedded into the gabbro dust. The dust is very fine, as produced during diamond sawing of dust of gabbros. And show you the next one, just how we built this. This you see here on the left, the students preparing the tray. In front, you see the copper mesh already mostly covered with the dust, and we are creating a uniform layer. And then on the right side, we insert this into the box and have then install a, on the left side you see a stainless steel mirror that reflects the light coming from a welding arc, which is on the left side at the bottom. And that light will be projected onto the stainless steel mirror and will be from there reflected onto the surface of the dust. And in the middle you see while the arc is burning. So in the moment we turn the spark on, the welding arc on, we see an increase in the current, and the current flows from the illuminated part through about 80 centimeters of a 1 centimeter thick layer of fine gabbro dust to the unilluminated side. So we have confirmed, which we knew already ahead of time, that dust is able to transport the current because these positive Hall charge here being associated with the oxygen sublattice, wherever there's grain-grain contact between the materials, they are able to flow. So we can say we have confirmed that UV activation takes place. If peroxy effects exist in the material, and that the positive Hall charge here that are activated by the UV light can flow through dust, and they are presumed to be able to also flow through the lunar regolith. So we would like to make a proposal for a device that could be incorporated into, for instance, a lander, into the leg of a lander, and then as the lander settles down on the lunar surface, would penetrate into the lunar dust, into the lunar regolith, and the details, of course, have to be discussed. And then we would, if there is a place where the terminator, the morning terminator, is coming in the way it is sketched here, hiding behind a not too distant mountain, so that over time the terminator will move through this site. We will be able to measure a current between the central pin that would in contact with the regolith below the surface, 10, 15 centimeters below, and a contact that is at the surface itself. If it is possible to have a second device of the same type, separated at a distance as far as practical, we could actually then make an even better experiment as the terminator moves over the site. We will see first a voltage and also then a current building up between these two electrodes as a function of UV illumination. So the expected results is that as the terminator approaches, we expect to see a voltage building up between the surface and the below surface contacts, and that should happen already when the terminator is still kilometers away from the site. So the challenge is to be able to measure, do an electrical measurement that does not require much energy at the end of the lunar night, and have the power to do this experiment. Also, there will be a voltage building up between two contact points separated by a distance d from each other and a variable distance d from the terminator, so that when the terminator moves on, it will first hit one and then the next. So in summary, we see a possibility to measure voltages between surface and below surface contact points in a regolith across the morning terminator. This will increase our fundamental understanding of the moon and its origin. It will provide insight into electrical properties of the lunar regolith and lunar rocks. And it will, because it has also implications from the medical side, it will help plan for human presence on the moon. Thank you.